secular, moves on secular orbit of radius 7,000 kilometers above the S, round the S, above the S, and then it orbits the S. The satellites orbit the S. Assume the shape of the S to be a sphere. Assume the shape of the S to be a sphere. A sphere of radius 6,400 kilometers. So then now, calculate total energy. Hey, my dear student, remember the concept I taught you. Can calculate the calculate the total energy required to place what in a satellite, place a satellite in its own orbit, from the S, given acceleration of gravity is equal to 10 Newton per kilograms or meter second squared. So that's the question, right? Right. Try to think how you can solve that problem with the reference of what I taught you in the previous lectures. Let us read the question first. A satellite of mass 1,000 kilograms moves on a circular orbit of radius 7,000 kilometers above the S, and it orbits the S. Assume the shape of the S to be a sphere of radius 6,400 kilometers. Calculate the total energy required to place a satellite in its own orbit from the S, given that acceleration gravity is 10 meters second square. I like this question because it will testing understanding of a student concerning about gravitational potential energy. And if you want to realize, let us solve, let us go together. But you can try. You can pause the video and try to solve yourself. And then after, when you are done, you can continue to watch the video to see the solutions, how you should solve this problem. You have to try. That's how I used to learn. I don't run quickly and look the solutions or how the problems has been solved. I used to think myself and try myself, then I'll go and do corrections. That's how I do self-learning. And really, I tell you that it brings clear understandings about the concept. So solution. So we'll be following a number of steps on solving this problem. The first step, okay, so you can, yes, you can start with data given first to simplify the problem first because it's a little bit complex the way it is. Mass of the satellite, and this one will have notations of M, is equal to 1,000 kilograms. Then its orbit at a radius of 47,000 kilometers. So the radius, not the height, radius of what? Radius of the orbit. Radius of the orbit, let's say R, right, is equal to 7,000 kilometers. So if you compare the radius of the orbit and the radius of the S, this is larger than this. So interesting. Again, we have radius of the S. Radius of the S, this we can use this notation, is equal to 6,400 kilometers. Again, what are we given? The total energy. Calculate the total energy required. So we have total potential. So total gravitational energy, total gravitational energy, total gravitational energy, which is 80. This is what required, right? Required. So that's what we are looking for. That's the first step. We are given also acceleration gravity, which is 10 meters per second square. That is a fundamental step. Let us go to the second step. So the second step in physics, and even in just mainly in physics, whenever you be given problems, think about how you can sketch the problems, sketch diagrams, to simplify, to see where can you start from. So the second step, we say that is sketch the problem. So let us sketch the problem. So I will sketch first of all the surface of the S and it's the center. So this is the mass of the S. So this is the 1 point above the S. And then suppose that this is point A. Again, we have an orbit. Listen carefully. Look careful this sketch. So this is the orbit. So this is point B. Suppose that this is point B, and remember that we have, because we need the total energy, we have, let's say, mass A, mass at point A, mass of the satellite, and also here we have mass of the satellite, right? We might call it MS or even just lowercase m. So listen carefully. The radius of the S is the distance from here to here. This is what we call the radius of the S. But again, we have what we call the height of the orbit. Okay, the height of the orbit, not above the S surface. From the S surface, this we have notations of R. So what is this? This is, we call it satellites. Satellite's orbit. What is this? This is Earth's surface. Earth's surface. Right? So what is this? This is the satellite. So this is the satellite orbiting what? Orbiting around the S. So what do you find here? Here you have to be careful. Remember that we used to carry satellites by using rockets. And when a satellite has to orbit the Earth at a particular orbit above the Earth's surface, then it has to be taken first to the Earth's surface, and it will be given the initial velocity, or the initial velocity called just velocity, and then enjoy its life in its orbit. So listen carefully. So you have how many points? You have 2 points. So it means that the questions ask you that calculate the total energy means that calculate the total energy required to place a satellite in its own orbit. So total energy to move the satellite from the Earth's surface to its own orbit. So there we have to go to steady state. Right? Steady state. So first of all, that we say that let us reduce what? The potential, the formula of what? Of potential energy and the gravitational kinetic energy at 20, at point A. And point A, we mean that at the Earth's surface. At the Earth's surface. What does it mean? Listen carefully, because physics is beautiful. Remember that energy is conserved. It means that when you say energy conservation, so you say that energy cannot be created nor destroyed. Energy can neither be created nor destroyed, but can be transformed from one form to another form. So it means that when a satellite is removed from the Earth's surface, or at the Earth's surface, the satellite will have a particular amount of energy. Right? And then when it's moving towards the point B, to reach point B with particular amount of 40 of energies. And these energies we have 2 types of energy: potential, gravitational potential energy, which depends on what? On height, and also we have kinetic energy, which depends on what? On velocity of the satellite. So we say that at point potential, let us start with potential energy at point A. The potential energy at point A here, it will exist first of all. So it will be what? Mass of the satellite times mass of the Earth times what? Universal gravitational constant divided by what? By the radius of the Earth. This is the potential energy at point A, right? Where potential energy at this point. The distance from the center of the Earth is right. Right? I taught you in lecture 8 how to write gravitational potential energy. So this is the formula. The thing is, you have only to notice is to know the sign. We say that this should be what? The sign should be negative. Right? Okay, so that is what the formula of potential energy. Again, we say that the kinetic energy at point A. Because the satellites is not, listen, the satellites will move when it reaches point B. And when we take a satellite from the surface to point B, then remember rocket will give its initial velocity equal to orbital velocity of 3 kilometers per second in order for it to circulate if this is the stationary satellite. Okay? So bear that in mind. So the satellites will be moving when we reach at this point. So what is moving from point A to point B is just a rocket. This is not an orbit. The satellites move when it reaches this orbit. Bear that in your mind. So kinetic energy at point A, for that case, is equal to 0 joules. No any motions of the satellite. So kinetic energy of the satellite at point A is equal to 0. So then total energy at point A, on the Earth's surface, will be equal to the potential energy at point A plus kinetic energy at point A. So the total energy now at point A, this is equal to what? Negative mass times mass of the Earth times universal gravitational constant over radius of the Earth plus 0 kinetic energy. So we say that the total energy at point A, this is equal to what? Negative mass of the S, mass of the satellite, times universal gravitational constant over radius of the S. Right? Radius of the S. Okay, good. So that is one of the formula, so we can call this one as equation 1, because we defined. The first step now, we say that reduce what? Reduce the formula of 40 of potential energy at 20 B. So when the satellite reaches its orbit, what will be the potential energy? So potential energy at 20 B will be also negative, still negative, mass of the satellite, mass of the S, which is universal gravitational constant, but now the radius is no longer the radius of the S, this R. Right? Why? Because we take a reference from this point to its orbit, or from this point to this point. So suppose that, I can call this equation 2, but don't need it currently. So we go, then we got the fifth step. We say that reduce formula of 40 of kinetic energy at 20 B. So we say that kinetic energy at 20 B, this is equal to what? So remember that I told you how to derive the kinetic energy, gravitational kinetic energy. So I told you. So when we did the derivations, it was we obtained negative mass of the satellite, as mass of the S, times the universal gravitational constant over twice. For this case, because it's 20 B times R. Right? So then at the fifth step. So we go dirty to the sixth step. To the sixth step, we say that reduce the formula. You see the beauty of physics here? Reduce the formula of 40 of total energy at 20 B. Use the formula at 20 at 20 B. Total energy at 20 B. So total energy at 20 B is total 20 B is equal to potential energy at 20 B plus kinetic energy at 20 B. So then we say that the total energy at B is equal to potential energy, negative mass, mass of the S, universal gravitational constant over R, and then plus what? Is potential energy negative? No. Kinetic energy is not negative, it's positive. Remember the way we derived. It's positive, it's not negative. So negative mass times mass of the S times gravitational constant, and then here we have mass, mass of the S, is universal gravitational constant over twice R. Right? So it means 1 minus, or 1, it is a half minus 1. So the total energy, 20 B, in this case, you have to find the LCM. What the LCM there? It is 2R. 2R over R is equal to 2. Multiplied by this one, it is negative mass, mass of the S, times universal gravitational constant. 2R over this one is 1. That's what the mass of the satellite, mass of the S, times universal gravitational constant. So total energy at 20 B, negative this one, these are the same physical quantities. So we remains is negative mass, mass of the S, universal gravitational constant over twice R. So this is not the total energy for the whole system that required with the satellite. This is the total energy at 20B. Interesting. Remember that I gave you warning at the beginning of solving this question. So you got the 7th step. You have to continue solving the same problem. Now we say that use the formula of what? Of determining the change in what? The change in total energy, which we've been asked me to find. Total energy of the satellite from what? From point A to point B. Total energy gained by the satellite to move from point A. The goodness of solving problems by following steps. In each steps I write what am I doing next. So it will be very simple for you to use my notes in your review because you don't need my presence. Okay, so you say that now change in total energy, E total, is equal to what? Is equal to total energy at 20B, the highest point, minus total energy at point A. So change in total energy. This is equal to what? Energy at point B, the total energy at point B is equal to negative mass of the S. So suppose that this is the second equation. So divided by what? Divided by twice R minus total energy at point A. Total energy at point A is this one. So we say minus negative mass of the S, universal gravitational constant, over radius of the S. Fantastic. Hey, physics is beautiful. Then, if that's the case now, we say fine. So we have what? Change in total energy. And this one will be negative will be positive. So we have what? Mass, which is constant, mass of the S, gravitational constant, and then in bracket we'll have what? Negative 1 over 2R, then plus what? 1 over RE. Right? Interesting. Okay, so let me rewrite it here. The change in total energy between point A and point B is equal to what? Is equal to mass of the satellite times mass of the S times gravitational constant, then negative 1 over 2R over negative over 2R minus 1 over radius of the S. Right? Radius of the S. So this is positive, according to what? So I just copied this formula at this point. Next, we have to add. We have to know add the fraction there, which is the subtractions. So to add the fraction there, it's simple for A-level student. So mass is mass of the S, gravitational constant, and then here we have denominator, which is what? Is equal to 2 radius times radius of the S. That's the denominator. So take this over this, you get negative radius of the S, and then this over this over this, you get 2R, so plus twice R. So this is the formula. So then now we continue. Change in total energy between point A and point B. For this case now, it will be what? We might say that it will be twice mass of the S times G divided by what? Times R divided by what? By twice R, then radius of the S. Hence we say what? Minus what? Minus mass of the satellite mass of the SG, radius of the S of what? Twice radius of the S. So what I've just take this product of constant, I multiply with this one, that's what I wrote here. Then I took this one, I multiply by this one, that's what I wrote here in numerator. So then we can simplify them if you're interested. So such as this and this. And then so you can cancel this and this, you can cancel this and this. So you see, you might have what you had there. So change in energy, or in total energy, is equal to mass of the S times inverse of gravitational constant. And then we say that, yeah, so that's what we had there. So 1 over RE minus 1 over 2R. Okay, so if that's the case now, the next step, we say that, okay, are we given the value of gravitational constant? Universal gravitational constant? No. What are we given? The value of what? Acceleration due to the gravity, which is 10 meters per second square. So we are not given, this is the final formula, but we are not given what? The value of universal gravitational constant in the question. Also in this question, we are not given the mass of the S, so that is not the suitable formula. We are not given the mass of the S. What are we given? I have summarized in the data given. We have been given the radius R, the radius of the S, and acceleration gravity, and the mass of 40 of the satellite, which is 1,000 kilograms. So let us enjoy the beauty of 40 of physics, right? How? So this is the case. So now we were in 7th step. Now we are going to the 8th step. So the 8th step, you have to recall what I taught you in previous lectures of gravitation. That you recall the relationship, because we are not given. Make sure that you use the constant which you have been given. If any constant is not given, it's better to leave its symbol or its later there, rather than say that I know the value of this constant. So if the constant is not given, think again outside the box. How can you solve the problem? So this is the subscript, E subscript. Remember that relationship between what? Between universal gravitational constant and acceleration due to the gravity G. What did we say? I told you that the products of mass of the S times gravitational constant is equal to acceleration gravity times radius of the S. So for our case right now, the radius of the S is RE squared. Okay. So this was the second equation. So suppose that this is the third equation. So this is what? The third equation. And this is what? The fourth equation. So if that's the case now, we can take the fourth equations, substitute. So that the ninth step. Ninth step we say that substitute equation 4. Equation 4 into equation 3. Okay. So then if you substitute it, we get to the formula of change of total energy between 2 points on the S surface and on the satellite's orbit will be equal to the mass, then acceleration gravity, radius of the S square. Okay? You may use either this formula or you may use this formula. Any of the formula will give you a response. You prefer, so let us prefer this one. So then we have what? I think the best one is this. So the question 3, because these questions and these questions are similar, this is equation 3. So this is equation 3. I don't have a space there, right? So the equation 3, inside the bracket you have radius of the S, then plus what? Twice of radius of the satellite's orbit over twice times radius of 40 of the S. Now we continue to enjoy the beauty of physics. Physics is beautiful, my beloved student. Okay, so we say that change in total energy is equal to what? So for that case, is there a negative? No, negative. 2, so there we have 2, okay, fine. So this is equal to what? So let me copy it. Change in total energy between the 2 points is equal to mass of the satellite times acceleration gravity, radius of the S square, and then in bracket we have negative radius of the S, and then plus what? Twice radius of the orbit of what? Over twice radius times radius of the S. So what happens? So radius of the S, one radius of the S, and one radius of the S will cancel, right? So you say that change in total energy between the 2 points is equal to mass of the satellites which we are given, times what? Times acceleration gravity G we are given, radius of the S also we are given, minus what? Radius of the S we are given, radius of the orbit we are given, and then we say what? Over twice R. So this is the final formula to solve our problem. So we go to the 10th step. So 10th step, we say that now let us compute the total, say total, the total energy, okay, the total energy required by the body, the total energy of 40 of the body, total potential or gravitational, the total gravitational energy, the total gravitational energy. Now we can compute it according to the constant that you've been given, not according to the constant that you know. Use the constant that you've been given. So according to the questions, the acceleration gravity will be given as 10, not 9.10, not 9.8, don't cram. And then the radius of the S is 6,400 kilometer. So this is exponent 3 meter. And then we multiply by what? Negative 6,400 exponent what? Exponent 3 meter plus what? Twice. What the radius of the orbit will be given? 7,000 kilometer. So times 7,000 kilometer, 7,000 kilometer exponent 30 exponent 3 to change it into meters. And then we divide this what? Twice times 7,000 kilometer, which we change into meter. So this is the expression. So meter cancel. Then we remain short. This is meter per second, so we begin with this is Newton per kilogram. Acceleration of, is it Newton? Acceleration? Yes. Newton per kilogram. So this is Newton per kilogram. So for Newton per kilogram, so you have Newton meter per kilogram. Do you have any other kilogram? Yes. We have to multiply with certain mass of the S. So I forgot some constant. So let me write clearly, so I might not leave any constant. Okay, change in the energy is equal to what? It begins the mass of the satellite, 1,000 kilogram, sorry, not kilometer, 1,000 what? Kilogram, excuse me. Acceleration gravity, we have been given 10 meter per second square or 10 Newton per kilogram. Understand that? 10 Newton per kilogram. And then we multiply with what? We multiply with the radius of the S, which is 6.4 exponent 6 in other words. And then we multiply with what you have in the bracket, which is negative 60.4 exponent 6 meter plus what? Plus twice times what? 7 exponent 3 meter, and then the denominator that we have is what? Is twice times what? 7,000 exponent 30 times 3 meter. So I told you that this meter cancel. Kilogram and kilogram will cancel. So it means is what in Newton meter, because this is meter. So unit of this radius of the S is meter. So you have Newton meter, and Newton meter means what in joules. Physics is beautiful. Then now it's